All right, everyone, we had a bunch of homework assigned from various days last week, finally all due today after we finished our activity yesterday here. First bit of homework that we had assigned last week was worksheet number 2, impulse. So we had a request to go over questions 6, 7, and 8 from that worksheet, so we'll do that now. Starting with question number 6, which I think might be the hardest one on the page, maybe. It says a 1 kilogram ball traveling towards a soccer player at a velocity of 5 meters per second rebounds off the soccer player's foot. I'm going to underline that in red or circle it in red or maybe buy an ugly highlighter and highlight it in that ugly colored highlighter to draw attention to that. Why is it, do you think, that I wanted to draw attention to that one little phrase there, or even that one little word, rebounds? Even before I finished the question, I drew attention to that. Why do you think I might do that, Matt? Okay, it implies a change in direction. And when we have a change in direction, Parker, what do we always have to be conscious of? Positives and negatives, right? If it's changing direction, something's going to be positive, something's going to be negative. Doesn't really matter which one is positive, which one is negative, but the bottom line is something's going to be positive, something's going to be negative. 8.5 meters per second. The time of contact is that value. What's the force applied on the ball? So we're going to write down some givens here now. That's mass. This is going to be VI. We'll make away from us as positive. That means that this is going to be negative, right? If it's going towards us, it's negative. If we defined away from us as positive. Could you have done it the other way around? Sure you could have. Sure. We could have made towards us as positive and away from us as negative. Doesn't matter as long as you're consistent. This is going to be VF, and it's going to be positive because it's going away from us. This is going to be the time, and we're looking for the force. What kind of a question is this? What kind of a question is this? What concept are we going to use to answer this question? Joey? Impulse. Why do you say that? Besides the fact that it says impulse at the top of the page. Force and time. Good. When you see a force and a time, that implies there's an impulse, right? You apply a force for a certain amount of time, the velocity will either increase or decrease. The momentum will change. It's an impulse problem. So we're going to write down that equation. Delta P is equal to F times T, and it's equal to M times delta V. F is therefore equal to M times delta V over delta T. The mass here is 1 kilogram. Delta V is VF minus VI. VF is 8.5 minus VI, which is 5, divided by the time of 2.0 times 10 negative 2 seconds. Is that right? Joey, what's wrong? Good. Should be negative 5. That's why I circled that in red up here, right, to remind me that something's got to be negative. Something's got to be positive, something's got to be negative. It's not good enough to just say 8.5 negative or subtract 5. It's 8.5 subtract negative 5, which obviously gives me a different answer. Can you do the math there? That should work out to be positive 675 newtons. Why positive? Well, mathematically it worked out that way, but we defined away from us as positive, and of course the force should be away from us if you're going to change the direction of that ball. If you defined towards us as positive, what would you have gotten for an answer? Negative 675. Both would be correct. You just have to recognize what the positive or the negative, whichever one you get, means. Okay, let's take a look at number 7 now. 7 says, a 1.5 kilogram rock falls from the top of a 10-meter high building, strikes the ground below. What's the impulse experienced by the rock during its fall? Well, it's clearly an impulse question, right? Because it asks us for impulse. Not rocket science there. Now, it's not an easy question, but it is easy to determine what to do. It's impulse. We've got a mass here of a rock of 1.5 kilograms. What do you want to call this? This 10-meter high building? Parker? Call it displacement. If we're going to call it displacement, we're going to make it negative 10 meters, right? If we're going to call it initial height, we'll make it positive 10. Now, if you're calling it height, you're probably going to use mgh equals 1/2 mv squared. If you're calling it displacement, then you're probably going to use vf squared is equal to vi squared plus 2ad. Okay, we're looking for the impulse that it experiences during the fall. Okay, let's get the velocity of this rock when it strikes the ground at the end of the trip. Vf squared is equal to vi squared plus 2ad. Now it falls from rest. It should say from rest, but that's what I meant. Anybody have the value of Vf there? How fast is it moving when it reaches the ground? Yep. 14.01 meters per second. Now that's the final speed. Technically the final velocity wouldn't be 14 meters per second. It would be negative 14. So I solved for final speed, and then I just wrote down underneath it the final velocity is negative 14, just to remind me, okay, maybe it doesn't matter, maybe it does. Yeah, I'm going to write it in just in case. Okay, now the impulse experienced as it falls is equal to F times delta T. It's also equal to M times delta V. Looking for impulse. What other part of the equation do you want to use, Ft or M delta V? I got mass. I got Vf and Vi, right? So let's use M delta V. M is 1.5 kilograms. Delta V is a final minus initial. Final is negative 14.01. Subtract initial, which is 0. We do the math there for question number 7. That should work out to be a delta P, or an impulse, of negative 21.0 kilograms meters per second, or negative 21 Newton seconds. Anybody do it differently and still get the correct answer? Because I see one more option here. One more like completely different option. Not just, EI equals EF, mgh equals 1/2 mv squared, but a different option entirely. Anybody have this thought? Anybody think of trying that one? What would F be? What would the force be on this rock as it falls? Andy? Yeah, it would be 1.5 times negative 9.81. What would the time be? Well, we don't know. We would have had to find the time, right? Maybe going A is equal to delta V over delta T. Okay, solving for T. Maybe going D is equal to VI plus VF over 2 times T. Solve for time some other way, and then plug it in there. When you do that, what do you think you get for delta P? If you try something 2 different but legitimate ways, you're going to get the same answer both ways. It's not a coincidence. If this equation is valid, if it's real, if it works, then it shouldn't matter which part you use, as long as you have enough givens to put into it. Okay. This would be my preference right here, okay, but the other way is fine as well. Just becomes a little bit more work. All right. 8 says a 1.5 kilogram rock. Wait a second, same question, isn't it? Strikes the ground below. Oh, what's the force of the ground acting on the rock if it comes to a stop in 0.350 seconds? There's not a whole lot of work to do for question number 8. Don't we know the impulse already in question number 8? What's the impulse imparted to the rock by the ground? Who's got that number for me? Quick. Okay, Katie says we use the one from number 7. So it would be negative 21.0 kilograms meters per second. Is that right, guys? Who says yes? That's correct. Who says no? That's incorrect. Well, it's real close. It's real close, but not perfect. What did we just solve for, Ken? What did we solve for in question number 7? As it falls. What do we need in question number 8? Not the impulse as it falls, but the impulse as it stops, right? So that's going to be right, because it requires an upward force to stop it, right? Upward force, upward impulse, or positive impulse. So we're going to make that positive 21. Bottom line is, if it gained 21 kilograms meters per second downward on the trip down, then it loses 21 as it stops. Okay? Loses 21 downwards, which makes it a positive value. So delta B is positive 21 kilograms meters per second. Okay, we got a time here of 0.350 seconds. We're just going to say impulse is equal to F times T. Now, careful, this F is not the force of gravity like it was in that second method that I told you for question 7, because this is the collision with the ground now, not the fall, but the collision with the ground. F is equal to 21 over 0.350, and when you do the math, it works out to be positive 60.0 newtons. Logically, it should be a positive force. You can't stop an object that's falling downward by applying a downward force. It has to be an upward force. And we got an upward force. We got positive 60. Good there? Any other questions on that worksheet? For number 9, I got 20 Newton seconds for the impulse, which of course, as soon as you see that graph, what should you think? 3 words. As soon as you see that graph, I don't care what you're asked, 3 words. What are they? Area equals impulse. Good. Now, if you calculate the area of that graph, let's scroll down there. Calculate the area of that graph. Doesn't matter that it's not a right angle triangle. The area of that graph is simply going to be 1/2 base times height. 1/2 of, we got 10 here. We got a height of 4. Now, this one's a bit easier because you don't have any strange units here. What you'll often see is, say, milliseconds on the bottom or kilonewtons on the side or something like that. Okay, be aware of that if you do. Okay, here we don't. Multiply those together, and we get 20. The units would be either kilograms meters per second or Newton seconds. We're asked for the change in velocity. We can use m times delta v. We don't want to use this. Okay, we don't want to use this equation with this graph. Anybody remember why? It was last week that we talked about this, but why can't we use F times T with this graph? We can use m delta V, but not F times T. What's the problem? What's F stand for? Shannon, what's F stand for there? Force? What's the force? What's the force in that graph? Oh, what's the value of the force in that graph? Tough question, right? That's the problem, right? That's the problem. The force is changing. So what value would you put in for F then? Well, technically, you could put in the average force, but how are you going to find the average force for this graph? Okay, don't even bother. Don't even bother trying to use that equation. M delta V works because the mass isn't changing, and delta V accounts for the change in velocity. F doesn't. So don't bother putting that one in. All right. We're looking for delta V here. We get delta P over M. Delta P is 20, as we just found, and M is 4. So that becomes a change in velocity of 5.0 meters per second. Here's one for you. What if I had told you VI was 3 meters per second? We didn't, right? But what if it had been? What if this was a multiple choice question on an exam? You were told that VI was 3 meters per second, and you were asked for the final velocity. What's the answer to that question? 8. I guarantee if that's a multiple choice question, one of your options is going to be 8, right? What do you think one of the other options is going to be? 5. And I guarantee you some of you are going to put 5. Guaranteed. Because you're not going to read the question carefully. You're going to look at it, you're going to calculate delta V, because that's what we do. calculate delta V. You're going to get an answer. You're going to see 5 as one of your options. You're going to pencil that one in, and you're going to get it wrong. And you're going to walk out of that exam thinking you got it right. Read the question, right? Know what you're being asked. In this case, it was change in velocity. Some other case, maybe it is the final velocity. Know what you're being asked. Yeah. I'm sorry? Well, it depends on what you're asked, right? If you're asked for the change in velocity, it's 5. If you're asked for the final velocity, then it has to be whatever your initial is, plus whatever you changed by. Oh, right. So it would have to be 5 plus 3 in that case, which is 8. Okay. The next bit of homework that we had assigned to us was page 462, a couple practice problems, both involving graphs like this. You might be okay with that since we just went over this question, but if we need to go over them, we will. There we are. Any issues with either of those questions on 462? Hey, notice 2C, a little bit different here, right? 2C asks us for the mass of the ball. We haven't done one like that, right? But it's the same thing, really, right? You get the area equals the impulse. The area equals impulse. You got the area. You got the impulse. Well, we now have delta V. Usually we have M given to us and we solve for delta V. Here we have delta V, and then we just end up solving for M. What do you got to be careful with in question C there? Beyond using the right equation, beyond doing all the math correct and so on. What do you got to watch out for in question C? What should I probably circle in red or highlight with my ugly highlighter color so that I don't make some kind of silly mistake? Change in direction, right? One's east, one's west. Okay, draw attention to that. I'll tell you now, you will see on your diploma exam and on your unit test hard questions. No doubt about it. There will be hard questions. Okay, this isn't a question that I would say is a gimme question. It's not a trivial question. You got to know your stuff to answer that question. But if you do know your stuff, you can get this question right. We have to get this question right. We can't make a mistake because we missed one was east and one was west. We can't afford that. Okay, there's enough hard questions that we can't afford to get that question wrong. We can get that right if we're paying attention. East and west. All right, the final set of homework that you had was page 467, number 1 to 13. Any issues with those questions, please? All right, we got 3 questions on 467 that we need to go over, 4, 6, and 13. Let's try number 4 first. What's the effect on impulse if the time interval is doubled? What's the effect on impulse if the time interval is doubled? Well, basically what we're looking for here, Matt, okay, you were saying you didn't really understand what they were asking for here. Basically what we're looking for here is what the new impulse becomes. Okay, so it's a variable value changing question, right? So we're going to say delta P is equal to F times delta T. So what's the effect on impulse if the time interval is doubled? Well, if you double time, then impulse is going to double, right? What's the effect on impulse if we reduce the force to 1/3 of its original magnitude? Well, if this one goes down, then this one is going to go down as well by a factor of 3. So it's going to become 1/3 of what it was. We don't know what the original value was, but we do know the new value is 1/3 of what the original value was. Okay. 6. Here's our karate question. Using the concept of impulse, explain how a karate expert can break a board. I've never done this. I've never tried to do this. I don't think I ever will try to do this with my hand or my heel or anything else. But people that do karate have told me that when you're trying to break that board, you don't look at the board. Do you do karate, Katie? Taekwondo? Have you ever broken boards? Have you? people have told me, Katie essentially just tells me the same thing here, right? People have told me that you're kind of not, if the board is right here, you're almost not looking at the board. You're looking at the pen that's on the desk there behind the board. So you're aiming at that. You're pretending the board's not there almost, and you're using your body weight to give it more momentum, right? You're using your body weight, and you're going towards that pen that's behind the board, that point behind the board. What does that do? That allows you to follow through, right? So you're applying as much force as you humanly can, but you're also applying that force for as long of a time as you can. If you increase the force, it increases the impulse. If you increase the time, and that's what you're doing by trying to hit the point behind the board as opposed to trying to hit the board itself, then you're increasing the time, increasing the impulse again. The more momentum you can give to that board, at some point, the board isn't strong enough to hold that, and the board breaks. Right? So it's as, and I use this term loosely, it's as simple as that. Physics-wise, it's as simple as that. Now, to go ahead and do it, it's probably a lot harder than it sounds to go ahead and actually do it. Okay, let's take a look at number 13. Experienced curlers, Andy's our curler here, knows how to safely stop a moving stone. What do they do and why? Andy, what do you do when you stop a curling rock? Okay. Do you kind of cradle it as well too? Like, or do you kind of just put your foot there and it's like, and let it hit it? Oh, I see, like this. Okay, and then you probably move your foot back a little bit as it, yeah. So that, what does that do? Yeah, it's a predetermined impulse, right? That rock's going to stop. The impulse is predetermined. You want to increase the stopping time of that rock. What you don't want to do, the rock is coming this way. You don't want to just stick your foot out like this and have it hit it. What's going to happen? Andy, do you know what a curling rock weighs? It's about 20 kilograms, 19 point something kilograms. You guys know what that is in pounds? It's close to 50. Close to 50 pounds. You got a 50-pound curling rock. You got a 50-pound rock, and that's what it is, right? A rock coming towards you at, say, 7, 8 meters per second. It's going to break your ankle, or at least it's going to hurt your ankle a lot, unless you cradle it, unless you can increase that stopping time so that the force is dramatically reduced. Okay? It doesn't matter how you do it. Increase the stopping time, decrease the force. Even with your broom, right? I curled a couple times. Not very good at it, but curled a couple times. Sometimes I just took the broom and kind of cradled it back with the broom as it's stopping. Okay? Increase stopping time, decrease the force. Got it? So perfect. 2 questions here that illustrate both principles, qualitative principles of impulse. First one, the karate one, right? Where you want to increase the force, you want to increase the time, that increases the impulse. The second one, when you're stopping an object, you want to increase the stopping time, decreases the force, hurts less.